welcome to the fourth and final video in Unit 4, where we've been discussing the reactivity and structure of carbonyls, like you can see inside this ketone compound. Thus far, we've been focusing mostly on electrophilicity of the carbonyl carbon, and we've been paying a lot of attention to how the substituent groups that are attached to that carbonyl carbon will influence the strength of electrophilicity that occurs at the carbonyl carbon. So we saw how amides, for instance, are a lot less electrophilic than ketones on the basis of what the nitrogen, for instance, in an amide does relative to some kind of alkyl group of a ketone. So we're going to use a similar kind of a concept, but now we're going to analyze what happens at the oxygen. We'll be thinking about both nucleophilicity and basicity, because we notice that the oxygen has two lone pairs, and using one of those lone pairs to form a new bond allows the oxygen to be basic if it bonds to an H+, or nucleophilic if it bonds to really any other atom. But we could also talk about strength. It's not enough just to say oxygen is nucleophilic. It probably wouldn't be surprising at this point to say, like, maybe some carbonyl functional groups are more nucleophilic at oxygen than others, and it probably would also be unsurprising to know that, well, that's going to depend on what the substituents do to the oxygen, just like we assessed what the substituents do to the carbon. So to get started here, what I'd like to do is actually assess what makes something a good or a bad nucleophile. We've already done this for bases. We did this back in Unit 2. So nucleophile strength depends on the stability of the electrons that would be used when you're acting like a nucleophile. Stability of electrons to be donated. So another way of saying that is that as the lone pair, let's say, on an oxygen, like in a ketone, becomes stable, there's less of a driving force to actually take those electrons and move them into a bond. If the electrons are stabilized where they are, we shouldn't expect to see big radical structural changes happening very quickly. Another way of saying that is that what makes something a good nucleophile, what makes it good at that role, is motivation to actually stabilize electrons by forming a bond rather than holding onto the electrons themselves. So this is one piece of the puzzle, right? This electron stabilization. This should sound just like our argument for assessing conjugate bases, because it is. Remember that a conjugate base is a structure that's going to donate electrons into a bond to hydrogen. And if I destabilize those electrons, well, that makes the base stronger. Same exact idea, because the only difference between a base and a nucleophile is whether the electrons are being pointed at a hydrogen or some other atom. That's the only difference. So conceptually, nucleophilicity and basicity, you're allowed to think about those as almost equal. The other thing that matters here for nucleophilicity, and the wrinkle here, is that it doesn't matter as much for basicity as sterics. So nucleophile strength depends on the stability of electrons to be donated and steric hindrance. It's not enough just to have electrons that are really unstable. If you can't actually get close enough to anything that will accept those electrons, it doesn't matter, right? Your motivation is irrelevant. You have to be able to get to a position where you can actually do the thing you're motivated to do. So what we can say is nucleophile strength, I'm going to abbreviate it as nuc strength, goes up. Our electron stability is decreasing, and our steric hindrance is also decreasing. So these two factors drive nucleophile strength. If I make my electrons really unstable and really exposed, I'm going to have an amazing nucleophile. If I have really stabilized electrons that are buried inside of a structure, basically I would expect to have no kind of reactivity happening at that site. And unfortunately, most of the time, it's like you've got a little bit of both, like maybe some really unstabilized electrons, but they're also buried. So which factor matters more, sterics or electron stability, or the reverse? We've got some kind of very stabilized electrons, but they're white out in the open. Typically speaking, just like we said before, with electrophilicity, electron stability is going to be a larger driving force for explaining reactions. It's not that sterics don't matter, it's that if you had to pick one of these two features, this concept of electron stability will usually be a better way of understanding what we observe experimentally about different nucleophile strengths, but also making predictions about given structures, like what structure will be most nucleophilic. That becomes problematic when we have really significant steric problems. So again, things like butyl groups adjacent to reacting sites, things like that. Now in this picture will start to change a bit. But for most structures, it's usually going to be sufficient to just focus on electron stabilization as a driver for nucleophilicity, at least in a qualitative sense. So in the next section of this video, we'll be looking at, well, what exactly drives electron stabilization at the oxygen of a carbonyl? To parse electron stability, what we can focus on is buildup of charge. So this concept will be intimately related with buildup of electron density. As I start to pack more and more electrons into a small area, for instance, a single atom, those electrons repel each other, and you destabilize the structure, such that one pair of electrons might be better off in a bond. That's the nucleophilicity. In order to assess whether or not we're building up electron density on an atom, for instance, the oxygen of a carbonyl, we can use the tools that we've already developed. We can use induction, we can use resonance, and we can use hyperconjugation. So we can see that these concepts of induction, resonance, and hyperconjugation, these are kind of like tools in a tool belt. They all are important. We'll use them all for different kinds of structural features, and often we'll use all of them in the course of a single analysis. But these tools can be applied to a lot of different kinds of problems. We were using things like this to talk about acid-base chemistry and pKa's. We use these tools to explain or predict relative electrophilicity of carbonyls, and we'll use these tools to predict and explain relative nucleophilicity of the oxygen of a carbonyl. What changes is essentially what these tools are used to predict, where charge is building up and what kind of charge, and then how that buildup of charge influences behaviors. So that's essentially our explanatory framework for, well, all of organic chemistry, to be honest with you. The trick is to get good at it and to get fast at it. You'll find over the course of the semester that will most likely happen for you. So in the next section of this video, we'll be cleaning up the board a little bit here, and we'll start to look at actually applying our tools to first the structure of a ketone and analyzing nucleophilicity at oxygen, and then we'll look at a couple of other functional groups of carbonyl-containing compounds to see how their nucleophilicities differ from ketones. If we look at a carbonyl oxygen like you see here in this ketone structure, what we would need to decide is how much electron density is building up on this oxygen. There's a couple ways you can do that. One way is to analyze the structure that we would normally draw for a carbonyl, where there's a CO double bond and not necessarily any charges, in which case we would need to decide what the substituent groups are doing here. I'm going to focus just on one of the substituent groups, in this case just the methyl on the right, and I want to think about what it's doing to not only the carbon of the carbonyl, but also the oxygen. So I'm going to use the tools that I've developed of induction, resonance, and hyperconjugation. We know that there's not really any inductive effect here because of the nature of the carbon-carbon bond, so we'll say no induction. We know that there's no resonance because this carbon has no electrons that it can donate via a pi bond. But there is hyperconjugation. We know that this alkyl group is a hyperconjugative donor. So what that basically tells me is that we have a weak net donor. And that's to the entire carbonyl, not just the carbon that we were analyzing before. If I push electron density into this carbon by hyperconjugation, in this particular case, some of the electrons in the CO double bond, for instance, they might go closer to the oxygen, right? As you make this carbon electron rich, electrons in these bonds will move toward oxygen, and that makes the lone pairs on the oxygen a little bit less stable because we're starting to localize electron density on the oxygen. We could also look at that in the context of our minor resonance structure here, which I'll label. We could analyze the same methyl, and the same argument would apply. We still got a weak net donor, for the reasons that are listed here. And as we actually dump electron density into this positively charged center, or nominally positively charged center, right, there's less of a need to actually take electrons from this O- and move them into a pi bond. If I stabilize this positive charge by using the substituent as a donor, then the oxygen, or the electrons on oxygen, can just stay there. And basically what that would mean is that we, in the resonance hybrid, like the average of these two structures, we get a little bit more of this minor form contributing, and therefore a little bit more negative charge building up on the oxygen. So another way of saying that is, if the substituents stabilize the carbocation in our minor resonance structure, that minor resonance structure contributes more strongly to the hybrid. And in turn, that means that the hybrid has more negative charge character on oxygen. Right, so we've talked through that in a couple of different ways, written it as a paragraph essentially here. But you'll notice something kind of interesting. What we're really focusing on, even though we're nominally analyzing the oxygen atoms of carbonyls, we're still using structural analysis to assess what's happening at the carbon of the carbonyl. And then saying, oh, well, if I make this carbon electron rich, there's no reason for this oxygen to like push electrons back toward that carbon. The oxygen keeps them. And if it does that, it's more nucleophilic and basic because we're localizing charge in that place, right? That sounds to me like there's a relationship between electrophilicity of carbonyl carbons and nucleophilicity of carbonyl oxygens. So for a given carbonyl, so for a single one, as electrophilicity at carbon goes up, we basically mean to say that this carbon is becoming more positive. The nucleophilicity at oxygen would need to go down. So it seems like there's an inverse relationship between these. And that amount of electron density is going to be influenced by the substituents. So if the substituents are dumping electrons into the carbonyl carbon, the carbon is becoming less electrophilic. And because this carbon is becoming more neutral, I guess, from a charge perspective, this oxygen is maintaining more of its negative charge. Now let's look at that same kind of concept in a couple of other carbonyl functional groups. In this last section of the video, we'll tie everything together that we've learned in the unit by looking at 4 different carbonyl functional groups, all of which we've talked about previously: aldehydes, ketones, esters, and amides. But we'll actually do structural analysis for the variables between these. So that would be our hydrogen, our methyl, our methoxy group, and our NH2 group. Then we'll rank the relative electrophilicities, and then finally we'll rank the relative nucleophilicities. So honestly, the best thing for you to do at this point is to pause your video and populate this whole table. If it's going to take you quite some time, maybe 10-15 minutes, that's okay, but it's really helpful for you to actually engage with this. And then once you think you've got this table populated, then you can come back and watch the rest of this video and see how you did, right? So if that's what you want to do, pause now. So when I'm comparing a lot of structures like this, it's not going to be sufficient for me to say like resonance donor or not a resonance donor. And it's not even going to be sufficient for me to say like a strong resonance donor or a weak resonance donor. I'm going to have to actually compare for a single tool like resonance across all 4 structures at once. So what I'm going to do when I perform my analysis, I'm going to do one tool like induction for all 4 structures, and then I'm going to do another tool for all 4 structures, then I'm going to do another tool for all 4 structures. Then finally, after all of that, then I'll consider my net effects. So in the aldehyde, I notice that there's no induction here. this bond is not really polarized in a meaningful way. The same is true in our ketone, the carbon-carbon bond, not really polarized. And now I've got my methoxy group, so an oxygen, but looking ahead, I also am going to have a nitrogen. So of these two atoms, I know that one of them is a stronger inductive acceptor than the other because one of them, the oxygen, is more electronegative than the nitrogen. So this will be my strongest inductive acceptor. And I'm going to say that the nitrogen here is a strong inductive acceptor. So you can see how important this prefix denoting a comparison was, this EST. All right, that's going to help me when I go back to do my net effects, because I need to be able to have 4 unique net effects in order to do any rankings. Okay, so next we'll do resonance. We'll do it for all 4 of our structures, starting with the aldehyde. We notice that the hydrogen can't do any kind of resonance interaction at all, so no resonance. Okay, and then for the ketone, same thing, the methyl group, right? The carbon here can't form a pi bond, be a resonance or anything like that, so no resonance. And again, my methoxy group and my NH2 group, I need to make a decision about, of the oxygen or the nitrogen, which is a better resonance donor. I know they're both donors. We've talked about that before. So we know the nitrogen is less electronegative than oxygen, and they're about the same size, both second row elements. So we could say that the nitrogen is the strongest resonance donor, whereas the methoxy group is a strong resonance donor. Okay, so the strongest resonance donor for the NH2, strong. Resonance donor for the methoxy group. I'm just going to underline my EST again to make sure that we keep track of that since it's important. And then finally, I can do hyperconjugation. So not going to be present in the aldehyde. Yes, the methyl group here, as an alkyl group, is a hyperconjugative donor. I might need to qualify that. I might need to say stronger or weaker or whatever. So we can add that in if we need to. The methoxy group, really, if we're thinking about the oxygen, there's not really a hyperconjugation effect here. So I'm going to say no hyperconj. And the same thing would be true for the nitrogen. Okay. So we've made a lot of decisions here, and now we need to basically distill these sets of decisions into a net effect. So if I look at the aldehyde, maybe this is a little bit straightforward. There's not really any effect from the hydrogen that I'm noticing. So I could say something like no net effect. All right. For my methyl of my ketone, I've got no induction, no resonance, and hyperconjugative donation. I don't necessarily know like how important this hyperconjugation effect is relative to resonance unless I have experimental data. In the previous video, we saw this. We actually looked at those half-lives, and we know that ketones are much more electrophilic than either esters or amides. So we could say something like, yes, hyperconjugation is donating, right? But if you take all of the effects in total and by comparison to these other types of functional groups or substituents, excuse me, we could say that the methyl group is a weak net donor. Right, so the hyperconjugation effect is not all that powerful, certainly not relative to resonance. Our methoxy group now, we could say this is overall going to probably be a fairly strong donor. The resonance effect we know is going to dominate over the inductive effect. So we'll say this is a strong net donor. Again, the contrast between weak and strong is implying that even though both the methyl and the methoxy group are both donating electron density to their respective carbonyls, the methoxy group does it better, or to a larger extent. All right, finally the amide. Here we've reduced the amount of inductive accepting, and we've increase the amount of resonance donation. So if the methoxy group is a strong net donor, then the NH2 group needs to be a stronger, or the strongest resonance, or a net donor, excuse me. So we'll say stronger net donor. So being able to add this ER was reliant on deciding about these relative effects that we have underlined in red. All right, so if this is the case, we know that the carbonyl carbon of the aldehyde of these 4 carbonyls is the most electron poor, or the most positively charged, and that means that it's going to be the most electrophilic. Okay, the ketone is going to be, of the remaining 3 structures, even though it has a donor group, it's going to be more electrophilic than these other 2 because the donor is not as powerful. So this will be my second most electrophilic. My ester group, or the methoxy group here, it's a strong donor, but not as strong as the NH2 of the amide, so we could say that this is going to be the third most electrophilic, and then our amide is the worst electrophile of the 4. You can check this work. It's going to, if you go back and watch the video where we have half-lives for these different functional groups, you'll find that this is the order that you observe. Right? So far, so good. Now let's see what we can say about the relative nucleophilicity of the oxygen atom. Well, we know that if we're actually not really dumping any electron density into the carbon, that the minor resonance structure where there's a positive charge here is going to be extremely minor. We're not going to have very much electron density on oxygen relative to these other carbonyls, and that will make, even though the carbon here is the best electrophile, its oxygen will be the worst nucleophile. So here we're moving a little bit of electron density into the carbonyl carbon, and that makes the minor resonance structure where there's the O- a little bit more important. Certainly more important than the aldehyde, but far less important than we would see in either of our ester or amide cases. So here is our second worst nucleophile. Now we're starting to get some significant donation of electron density into this carbon center, right? We have actually seen resonance structures already that have an O- in them from the lone pair being donated from oxygen. So that would correspond to those kinds of arrows, right? We're going to be, you see how we're moving electrons onto the oxygen here? So now our oxygen is starting to get relatively electron rich, which makes it a better nucleophile than some of these other cases. But we know that that same effect happens for our nitrogen in the amide, and to a greater extent, because the nitrogen is the strongest resonance donor. That means that we're going to build up the most negative charge on this oxygen. The amide is our most nucleophilic carbonyl oxygen, and our ester is the second most. So you can see that there's a essentially clean inverse relationship between electrophilicity of the carbonyl carbon and nucleophilicity of the carbonyl oxygen. So that's kind of the good news. If you remember that, you can either just analyze nucleophilicity if that's what you like better, or you could just analyze electrophilicity if that's what you like better, and then basically think about, well, in my comparison, I'm just going to like invert all my ordering, and voila, you figure out the other reactivity mode. So this unit's jam-packed. We've done a lot. Remember, the key here is, 1, to understand the tools in the tool belt: induction, hyperconjugation, and resonance, how to deploy them. There's a lot of practice problems, some of them easier than others in the SLO. I'd recommend doing as many as you can stomach. No substitute for practice here, because the other place students struggle, even if they understand these discussions, is actually implementing this analysis in an organized way where things don't get backwards, right? So emphasis will be on writing things down as you go, having a process that you use the same way every time, right? So you saw me do it here in this section of the video where I analyze one tool for all my structures and then the next tool for all my structures. And again, once you practice, if you practice using that method and using the same method every time, you'll find that eventually it becomes fairly straightforward, even for more complex structures than we've been dealing with here. So that concludes Unit 4. In the next unit of the class, we'll be thinking about not just like carbonyl reactivity in a general sense, like electrophilicity or nucleophilicity, but looking at some specific reactions where carbonyls function as especially electrophiles.